So let's look at how we can identify intermolecular forces. So we're given a couple of substances, and we're asked to identify what intermolecular forces must be overcome in converting each of the following from a liquid to a gas. And it's basically just important to state it's in the liquid phase, because in the gas phase, you won't, for example, have hydrogen bonding interaction. You'll only have that in the solid and the liquid phase in water, for example. Um, but that's the only reason why that's important to note. So what needs to be overcome when something's in the liquid phase? So let's start with acetic acid. And with acetic acid, it's constructive just to actually think about what we have, and we can write out this formula a little bit. So it's a CH3 group, and then we know it's an acid, so it means it's a CO, and then there's an OH group bonded to the O. So essentially, I mean, whether or not you've had an organic course in your life before or not, you'll know something about it's kind of a structure that is linked between these C's. So there's a C here. It's a CH3 linked to a C. That C is then double bonded to an O, and that C is also bonded to an OH. And that OH is the important part, because that means there is a polar OH bond present in this molecule. So it's slightly positive, slightly negative. Right, and there's oxygen has two lone pairs. And this allows it to have hydrogen bonding. Okay, so even though you're not necessarily, even if you haven't had an organic course or whatever before, if you know that there's a polar OH bond, then you know that other molecules in interaction with each other will be able to form hydrogen bonding. So in other words, something will be able to orientate itself to have an H there and then form some sort of network with the rest of the molecules. I mean, and whatever, you don't have to draw this, but the point is that then you'll have other molecules also orientating their polar OH bond so that these interactions can then form. Okay, so that's the first thing that we were looking for, because if you see an OH or an NH or an FH, and your question is there a possibility of hydrogen bonding? So yes, in this case, let me just do that in black. So yes, there's definitely hydrogen bonding. That's the first part. Next thing, what is always present in all molecules? Well, that's London dispersion, or so-called induced dipole forces. So we can say there's also London dispersion forces. Of course, you could say forces. And then the last one is these molecules all have dipole moments. So you can see that all the oxygens are grouped together. So let me just draw a little. You can see the oxygen sits to one part of the molecule in each of these two cases. In other words, there will be a definite dipole moment for each of these two. All right. I hope that's going to delete just not everything that I've written now, but just enough so that I can get my nice picture back. But in any case, so that means we also have dipole-dipole forces, right? Okay, so that kind of gives us a way to do a checklist. We check whether or not there's NH, FH, or OH. If there's that, then we check whether or not there is a polarized bond which will allow for hydrogen bonding. If there is, then there's hydrogen bonding present. All molecules have London dispersion, or otherwise known as induced dipole, induced dipole. That's a given. So we can actually start there. Then hydrogen bonding. Then we check whether or not there is a dipole. If there is a dipole, then we have dipole-dipole forces. And lastly, if we have a mixture, which is not in this case because there's no mixtures here, then we can sometimes have that dipole-induced dipole, because one thing can have a dipole and something else can have an induced dipole in a mixture. Or maybe if you have a very large molecule, that means that's not necessarily something that you'll be can be easily identifiable. Right, so that's what we do. And of course, if there's an ion, then it will be an ion dipole. But those are options. That's what we're looking for. So with our tick box or tick list ready, let's look at the next one. So hydrazine, N2H2. So the question is, how does this molecule look? Well, we know nitrogen wants to form 3 bonds. So the best way to think about this is that you'll have it is H4, right? Yeah, H4. So there's 4 hydrogens, 2 for each nitrogen, and then each nitrogen is bonded once to each other because it wants to make 3 bonds. Right. So let's go through our tick list. All molecules have London dispersion forces. That's the first one. Second question then is it polar or is it non-polar? And it might be a bit of a question here. So is it exactly planar? Is it exactly flat? How does this molecule look? For your cases, it is non-polar, so hence there's nothing else of relevance here. So there can't be dipole-dipole forces. Last question, is there NF, NH, NF, NH, HF, or OH? And yes, there is an NH, and there is NH polarized bonds in this that can form hydrogen bonding interactions because there are lone pairs on these nitrogen. So yes, we will have then hydrogen bonding as well. Okay. What's our next one? Sulfur hexafluoride. Okay, so that's a Lewis structure that we need to draw. So that's sulfur in the middle. Three-dimensionally, you can quickly make it so sulfur will have 6 valence electrons. So you can put it 1, 2, 3, 4, 6, and fluorine makes 1 bond, and there's 6 of them. So you can quickly figure out that, well, we will have a situation where we will form an octahedral complex or octahedral structure. F, 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 not E, F, F. Right. And if you draw those perfectly, in principle, you're not able to do some fancy mechanics. It should be non-polar, right? Because the F should cancel with the SF, SF, there's no polarity here. So it's non-polar. There's no HF bonds or anything like that. So there's no hydrogen bonding and there's no dipole. In other words, because it's non-polar, the only thing that is present here is the so-called London dispersion forces. Or if you can just remind yourself, it is induced dipole forces. All right. And then finally, we have chlorine, which is Cl. Cl. And question is chlorine polar or non-polar? Well, it is non-polar according to first year chemistry. Maybe on a quantum mechanical level, depending on certain questions that you ask, you can argue it's not. You would say it's non-polar. So, and there's nothing else there. So, right. So it's because it's non-polar, it implies there's London dispersion forces are the only things present in it. Okay. So what's your maybe like a tick list for yourself? You ask polarity. Ask yourself for polarity, and then if it is polar, then it means it is dipole-dipole. If it's non-polar, then it means it's London dispersion or so-called induced dipole-induced dipole forces. Does it contain an OH, an NH, or an FH bond? And if so, is it polarizable? Question mark about hydrogen bonding. So then you can assess that for yourself. Then, are there ions? Are there ions? So meaning, is there sodium in the water? Sodium ions in the water? Because if there are, then it means there must be ion dipole forces. And then lastly, if you have a polar plus a non-polar molecule, you know that you will have dipole-induced dipole forces. So those are your options. And that's all you look for. Okay. So I think that's basically the most comprehensive summary. And that's why we don't test it technically directly. It's more common knowledge and useful to have so that you understand where on the chemistry on a more molecular level. Okay. Thank you for watching.